So, good morning from Melbourne, and thanks for dropping by to listen to our talk. I've taken the liberty of expanding the title a little bit to increase its perspective to include all of the components that are in electrolyte that are part of a green electrochemical process, recognizing a couple of recent pieces of work from our group where it was the whole electrolyte that we had to consider carefully in achieving the green and sustainable goals of the overall process. So I'm going to therefore talk about a couple of different pieces of work arising from our group in the last 6 months or so. The first is to do with the rather significant drive that there is around the world at the moment to find ways of producing ammonia electrochemically using renewable energy and thereby carry out the all-important nitrogen reduction reaction, or nitrogen fixation is another way to describe this process. And in this work, we've recognized that there's a need for a completely reversible, sustainable, non-degrading proton shuttle within the electrolyte that carries protons from the anode, where they're generated, to the cathode, where they're used in producing the ammonia molecule. And in this, we designed a phosphonium cation structure to do this job, and we'll look more about that. This was published recently in Science. And in the second part, we'll look at a new fluoroborate salt that has been designed for next generation lithium batteries, and specifically driving towards higher voltage in lithium batteries, and therefore increasing their energy density. And it's often the salt that is ultimately the limiting factor in the electrochemistry at high positive voltages in those batteries that we need to improve. We need to improve the stability of those salts in order to achieve the sorts of gains that are possible with the cathode materials. And that's a piece of work that was published or is being published recently in Advanced Energy Materials. The DOI is there. The work at the moment is still in press, but will be out hopefully by the time this conference actually takes place. And making best use of the this new age format of conference attendance that we have here, I thought I would let the two younger colleagues of mine in the group who've been very much part of leading the actual research in these two areas, actually let these two people present their works themselves and show their faces to an audience such as this. So first off then, I'm going to hand over to Dr. Karolina Matuszek, a senior postdoc in our group, who will talk about this nitrogen reduction work, and then she will hand over later to Dr. Binayak Roy, who is leading the novel salt work for next generation batteries. So first off then, over to Karolina.
Hi, my name is Karolina Matuszek, and I'm a research fellow at Monash University in Australia. And today I have a pleasure to share with you our recent research on nitrogen reduction reaction to ammonia, where we used phosphonium ionic liquids as a proton shuttle. And this study was recently published in Science. Ammonia is a globally important commodity, mainly used for fertilizers. Currently, its production, as you can see here in that figure, is far away from being sustainable. It uses fossil fuel-based materials, as you can see here, and it's very highly energy consuming, and therefore accounts for a significant fraction of a greenhouse gas emission. So you can see that decarbonization of this ammonia production is a very important task currently. Methane-derived hydrogen can be subsidized with water-based one that is obtained from water electrolysis powered by renewable energy. So let's say quite easy, but the hurdle really lies in the current ammonia production, so in the Haber-Bosch process. Alternative technology to this Haber-Bosch process is called electrochemical nitrogen reduction reaction. And that one can directly use renewably generated electricity, and it runs at lower temperatures and at lower pressures. So therefore, it actually meets the sustainable goals of the production. However, current reports demonstrate production rates which are much lower than the industrial targets. So we really need to focus to bring those numbers up to make this process being more being better than the Haber-Bosch process, so we can actually transition from that highly energy-consuming one. Among investigated modes of the nitrogen reduction reaction, a lithium-mediated process appears to be the most promising. And the mechanism of that process, which is shown here, is hypothesized to rely on a cathodic reduction of lithium ions in the presence of nitrogen to form lithium nitride. And this lithium nitride is then reacted with the proton source to form ammonia molecule. So ideally, those protons would come from oxidation of hydrogen or water on the anode, and then be transported by a proton shuttle molecule to the cathode, where this process would occur. Currently, research is focusing on ethanol as the sacrificial proton donor. It's sacrificial, which means it is not fully regenerated, and that really limits the performance and longevity of this process. So our goal was to develop a proton carrier that will be electrochemically stable and won't be consumed during the process. And for this purpose, we investigated phosphonium-based cations, as you can see here on the figure. And one of the example is trihexyl tetradecyl phosphonium cation. So these types of compounds are known to have a good chemical, thermal, and electrochemical stability. And additionally, they can dissolve high amounts of nitrogen, what was presented by our group a few years ago. And this is very important for nitrogen reduction to actually have this high solubility of nitrogen. Moreover, these structures are known in the literature for a long time from their reactivity. So the reactivity of those protons on the alpha carbon next to the phosphorus, which can be easily deprotonated. And the structure then which is formed is called an halide, and it's commonly used in a Wittig reaction. So in our process, reaction of the electrochemically generated lithium nitride with the phosphonium cation produces an halide, that's it, and the ammonia molecule. Halide compound is known to be very strong base, so it really gets reprotonated by the protons from the anodic oxidation reaction to regenerate the original phosphonium cation, and it can be cycled, as you can see here on the figure. But to confirm the capacity of that phosphonium cation to operate as this reversible proton shuttle, we perform a series of chemical experiments that simulates the transition between this phosphonium cation and halide. And we monitor this process using phosphorus NMR and mass spec. So as you can see here in the figure, the phosphonium cation produces one peak on the phosphorus NMR around 33 ppm, right? And after the addition of lithium nitride, this peak is shifted to 9.4 ppm, and this is due to the formation of halide. This value is in an agreement with the available literature, so that confirms that this halide is produced here. So okay, we got a half of the success, but the full success is to recycle that, so to reprotonate that halide. And in order to achieve that, we added a weak acid. In this case, we added acetic acid to simulate reprotonation of that halide, and that was successfully achieved, as you can see here. The peak at 9.4 fully disappeared, and peak at 33 ppm was fully regenerated. And to be sure that this actually works, we repeated that 3 times, and in every single time we got exactly the same results. So yes, that works. It can work as a proton shuttle. So in the next step, we use this phosphonium proton shuttle in the nitrogen electroreduction process. So cyclic voltammetric analysis demonstrated that the reduction of lithium ions in the presence of phosphonium cation is highly efficient. As you can see here in the figure, we tested a range of potentials, and in each case we produced ammonia. The best results we obtained for at minus 0.75 volts, and that gave a Faraday efficiency of around 70% and high ammonia yield rate of 58 nanomoles per second per centimeter square. Okay, so how this process look at the molecular level? So in the first step, the phosphonium cation, which you can see here, comes to the negative working electrode. And the negative working electrode is covered with lithium nitride. So when the phosphonium molecule reaches to the surface, it releases one of its protons to the lithium nitride and become an electrolyte compound and diffuses away. So then it clears the surface for the next proton to come that gives the proton, and so on. And 3 steps like this are required to produce ammonia molecule. And in the end, a positively charged lithium ions remain near the surface and are ready to form more lithium nitride. And again, the process is repeated. So this is how it works at the molecular level. But the next key step of that research was to demonstrate that we can run this process for a long, long time, right? So to demonstrate the long-term stability of the proton shuttle and the long-term stability of the whole system. So in order to do that, we carried out a series of experiments over 4, 8, and 20 hours in a constant current mode. So these experiments are presented here in the figure. They showed very stable operation of ammonia electrosynthesis system. And 20-hour experiment produces an average ammonia yield rate of 53 nanomoles per second per centimeter square at a Faraday efficiency of 69%. And this value is a really good value. It is a notable improvement upon the best reported system so far, which you can see here, where the authors of that paper produced ammonia at the yield rate of 30 nanomoles per second per centimeter square and Faraday efficiency of 35%. So to summarize the whole research, as I showed you, we proved for the first time that the phosphonium salts are highly efficient and reversible proton shuttle for nitrogen reduction reaction. They allow to produce high ammonia yield rate and Faraday efficiencies. Additionally, we confirmed their stability in a long-term experiments, achieving the best results so far, comparing to the other literature reports. And the results we obtained, which is even more important, I think, we obtained results in this work that are already in a practical zone. So they could be used in the industry, but currently we are working on their further optimization and scale up. So hopefully soon we will be able to provide that information. So thank you for your attention. And now I will pass over to Dr. Binayak Roy to talk about some of his exciting work on novel lithium salts for high voltage lithium batteries. Thank you again.
Thank you, Karolina. Hello, everyone. I'm Binayak Roy, and it's my pleasure to share my research here today. Here at Monash University, I'm working on novel fluoroborate salts for next generation lithium batteries. The major motivation of my work comes from the recent focus on high voltage lithium batteries, which are increasingly being considered for mobile and automotive applications. Now, unlike conventional lithium batteries, these high voltage systems work at a much higher potential, greater than 4.3 volt. Now, at this high voltage, the electrochemistry changes substantially, which the conventional lithium battery electrolytes fail to cope up with. This is where my research comes in. I'm working on identifying novel salts and electrolytes based on new anion systems so that we can address the challenges of high voltage chemistry and apply these new salts and electrolytes in high voltage lithium batteries and compare their performances against conventional lithium salts. Now, when it comes to conventional lithium salts, lithium hexafluorophosphate or LiPF6 is probably most well-known one. However, in presence of high voltage cathodes such as NMC, like lithium nickel cobalt manganese oxide, it's known to be quite unstable and not to mention its high toxicity and extreme sensitivity towards moisture, even at the ppm level. The other alternative conventional salt is lithium fluorosulfonyl imide. However, it's also known to show quite prominent aluminum corrosion tendencies, especially at high voltage. In my work, I have focused on a new family of lithium salt, lithium fluoroalkyl borates, and I have been particularly interested to explore the effect of terminal fluorination in the salts on various electrochemical behaviors, such as its compatibility with lithium metal, its electrochemical stability, its compatibility with aluminum current collector, especially at high voltages, and of course, its atmospheric stability. In my work, I have found this particular salt to be very interesting. It's lithium tetrakis hexafluoroisopropyl borate, or abbreviated as lithium BHFIP. Now, in literature, it has been shown to demonstrate high oxidative stability against magnesium and calcium systems. However, the lithium equivalent of this salt has not been reported in literature yet. In my work, I have seen two particularly interesting behavior of this salt, which is worth mentioning. The first is stabilization of the lithium cation by 3-DME molecule, which I think plays a major role in stabilizing the anion species itself. And the second one is the high terminal fluorination of this anion, which has a quite prominent effect in both battery cycling and its electrochemical behavior. Here, what we have done is understanding the compatibility of this salt against lithium metal. To do that, I have constructed a symmetrical lithium cell with the carbonate electrolyte of our novel lithium BHFIP salt, and I have cycled it in a symmetrical lithium cell for up to 1200 hours or 600 cycles. The symmetrical cell cycling didn't show any dendritic formation or any abnormality, suggesting the borate salt is perfectly suitable for lithium metal batteries application. I was more interested to explore its interfacial properties. So after 200 hours or 100 cycles, I have opened one of these cells and looked at the plated lithium surface by XPS depth profiling analysis. And what I found is, on the lithium surface, there's a rich formation of fluoroalkyl groups. However, after etching, I have found more inorganic species such as lithium fluoride and lithium carbonates, which suggests that this salt is able to form a ACI on the lithium surface, which includes both organic and inorganic species. This behavior is highly desirable for any electrolyte compatible with lithium metal anode. In the next step, I have been interested to explore the stability of this salt against aluminium. As I explained earlier, lithium FSI shows quite prominent aluminium corrosion tendencies, especially at high voltages. Here, what we can see is after an electrochemical experiment at 5 volt, LiFSI leaves behind prominent corrosion pits on the aluminium current collector surface. Now, the pitting behavior is lesser in case of lithium PF6, but still present. However, in case of our borate, it's nearly non-existent, which means that not only the borate salt is stable and compatible with aluminium at high voltages, but also it is also showing high electrochemical stability. So in the next phase, what I have been interested in doing is exploring its aluminium stability. So we have the instability of hexafluorophosphate is quite well known, and I have exposed a certain amount of PF6 salt under atmospheric conditions on a benchtop for 24 hours. And as expected, we can see quite prominent formations of HF or phosphoric acid, which probably would have resulted from the hydrolysis of PF6 salt. And then there is evidence of decomposition products forming in the fluorine NMR spectra as well. However, in case of my novel lithium fluoroborate salt, which was treated under similar condition, after 24 hours, I'm seeing in accumulation of moisture in the sample, suggesting that the salt does accumulate some moisture. However, it is not showing any presence of abnormalities or any decomposition products, either in proton chemical NMR shift, either in proton NMR spectra or in fluorine NMR spectra either, which suggests that this salt is stable under atmospheric conditions even after 24 hours. Now, this is a very interesting observation, but I was more eager to explore its physical significance in terms of battery cycling or electrochemical behavior. To understand that, what I did was constructing a LMO lithium metal battery with the exposed electrolyte after 24 hours. And as we can see in this figure, that the electrolyte, the novel fluoroborate electrolyte, even after its exposure, does accumulate a high amount of moisture, around 1600 ppm. However, the cycling behavior of the wet electrolyte is not very different from the dry one, suggesting that the salt, it is not only stable against moisture, but it also helps to limit the negative effect of moisture presence in a lithium metal battery. In the next phase, now we know that the salt is atmospherically stable, but under dry conditions, can our salt outperform a conventional lithium hexafluorophosphate salt? To understand that, I have constructed a NMC811 lithium metal battery. NMC811 being lithium nickel manganese cobalt oxide, a quite widely reported high voltage cathode materials in literature. And what we are seeing here, that the carbonate electrolyte of both salts, among the carbonate electrolyte of both salt, lithium fluoroborate salt performs much better than lithium PF6 in terms of both initial discharge capacity and capacity retention over long-term cycling. So to summarize, here we have a novel lithium borate salt, which can address the challenges of high voltage lithium batteries, which includes the corrosion tendencies, inhibiting the corrosion tendencies of aluminium at high voltage. And we have also seen this salt to be quite stable towards moisture and atmospheric conditions. And not only that, it also helps to minimize the presence of moisture in a lithium metal battery. This particular salt, we have found to have the properties which is highly relevant for high voltage applications. Therefore, the anion design strategy adapted in this work, it can inspire the synthesis of novel ionic liquids and associated salts, which I believe can perform much better in higher voltage batteries for their longer term stable cycling. I thank my co-authors and my colleagues for their help and support in this work. And special thanks goes to our research partner, Calix, for funding this research, and Store Energy for providing a collaborative research platform. I thank you all for listening to me. And now I hand back to Professor Douglas MacFarlane to wrap up our presentation.
So I hope you've enjoyed a quick look at a couple of pieces of work emerging from our group recently. Of course, acknowledgements in particular to our major funding sources, which are federal government agencies, as you see there, including our Center of Excellence for Electromaterials Science. And important to mention both the local companies, Calix, who are supporting the battery work, and Jupiter Ionics, a recent startup that is scaling up the nitrogen reduction to ammonia work that we've been talking about here. So thanks to all of them for their support and their vision. And of course, thanks to all of the people you see in the photograph here, who are the real workers in the lab. And you can see they range from relatively quite old, including me, to relatively quite young, as you can see in the center of that photograph. So thank you again, and we're looking forward to any discussion or questions that will arise in the discussion session. See you there.